Okay, so let's go here. So we're back in class. Sorry for everything. Hopefully that doesn't happen again this semester. I, don't plan on it happening again. But if it does, at least it's, if I can get feeling good enough to like not be sweating in bed, I can get up and kind of do those Zoom meetings, just like we would meet, regular class times. So we left off, and also I will start getting those Excels graded today. So Excel assignments you turn in, I'll start getting those graded today. So you might see some comments start popping up. I have my TAs help me with those. So I give them a pretty detailed kind of grading schema, but they sometimes aren't really sure what to do on certain things. So if you get a comment, but the grade isn't entered in, that likely means I'm probably going to end up kind of grading it and helping out with it. So don't freak out if it's there for a day or two with comments without a grade. Right? They should be probably done at the latest midtime next week. I expect probably sooner than that, but just to kind of not give you too much of a false hope that they might be done tomorrow or something. So let me minimize myself here. Well, hopefully, I don't know, on the Zoom, I got a little bit of feedback from some people. The whiteboard is kind of nice to see kind of via Zoom. So for those of us in person, I'm just going to start bringing this whiteboard with me in class. If I start writing some stuff up here and then you can't see it, I'm sure I'll be a lot more prone to kind of like stand up and ask you guys if you have any questions or kind of anything that I wrote down. But obviously you'll see it up there. It's a little bit smaller on the screen. And I'll probably do a little bit better job of just not leaving that little box up there, but completely switching to have a full cam. So everyone in here, you can't see what I'm writing on the board. It should be full screen up here as well, okay? We got a couple people waiting, so I want to get a little bit of talk out of the way because I figured there'd be a couple people kind of joining in late. So we talked last class about this complement rule. We talked about the addition rule, and we started to talk about this idea of the multiplication rule. So we'll talk more about this today. So this was the idea that if we had a conditional probability, also we talked about this, correct? We talked about conditional probabilities last class. Anyone that zoomed in? I want to make sure I'm not jumping ahead. I'm pretty sure we did that. I left off on that. Anyone wants to give me a confirmation? No one? I need a little bit of a head nod or something. What did we end on? What do you think we ended on? Did anybody watch the last class? Last Zoom? Yeah, okay. So let's see. I got anyone in the chat that's going to help me out. So from what I remember, I know we went over this complement rule. I know we went over this addition rule. I'll kind of revisit this multiplication rule here real quick. I'm pretty sure we went over it. But the general idea is if we're conditioning on something, what we're saying is that the probability that A occurs, right, is different if I have some additional piece of information. So if I look right here, this is what I would call the conditional probability of A, because we're conditioning on the fact that B has occurred. And we're saying given, right, the way we read this vertical line is given that whatever's on the right-hand side has occurred. So given that event B has occurred, what's the probability that we now see A occur, right? And that can change from the unconditional probability of A, which if we're thinking about the unconditional probability of A, what we're really thinking about here is, right, if I just have a marker that works, if I just have the unconditional probability of A, right, that could be very different than what we would call the conditional probability of A, right? We're conditioning on another piece of, so why would that necessarily be the case? Well, if you think about kind of experimental outcome space, maybe here's event A, relatively low probability of occurring, right? It's a pretty small piece of this huge kind of huge space. But now what if I tell you, here's event B, And now I say, given that B has occurred, so now I know I'm not in this huge experimental outcome space. Now I know that I'm confined to just outcomes in this circle B. Well, now it's much more likely that A has occurred, right? And so how much more likely? Well, I think what we kind of went through was, I believe I drew this for you. We had this idea, right? Let's say here is event B, right? Just that it's like half of the entire experimental outcome space. Right? I then have just kind of this upper rectangle here representing event A, right? So almost think about it as this red space, right? That's event A. Well, if I just look at what's the probability of A occurring, it's about 1/4 of that entire experimental outcome space. If I then say, well, given that B has occurred, now what's the probability A occurs? Well, given that B has occurred, I've essentially, you can almost think about, I've eliminated half of the possible experimental outcomes I could see. So now, given that B has occurred, now the probability I see A is about 50%, right? So it's greatly changed what that probability is. And really what we've done is we said, once we've limited it down to just, given that B has occurred, it's almost like the probability of A before. You can almost think about it as like the number of outcomes. Oops, sorry. You can almost think about it as the number of outcomes in A over like the total, where the total is just this entire experimental outcome space of 1, right? But now, once I've conditioned on B, this denominator is no longer the total number of outcomes. It's like the number of outcomes in B, right? And up here would be the number of outcomes in A that are also in B. And really what that is the intersection. So if we go back to this slide, really all I'm saying is the conditional probability, right? The probability of A conditioned on B, will no longer have the entire experimental outcome space of 1. Now we only have the experimental outcome space of B, right? Because I've been told B has occurred. Event B has occurred. So that's kind of my denominator now. It's the space I'm working out of. And what's the probability I see A? Well, now that I know that I'm in event B, it has to be wherever A and B overlap. So the probability I see where A and B overlap, that's the intersection. Right? So that's kind of the intuition behind why that multiplication rule works. If we just want to know for now that this is what it is, that's fine, right? You can just kind of accept the fact that this is the equation that we have for the conditional probability, but that's the reason why this equation works. So we can take that discussion and then start to push it further and talk about, well, now that we know how to find these conditional probabilities, we have this definition of events being independent, okay? So we talked last class about mutually exclusive events. So does anyone remember what was kind of, I mean, it doesn't have to be a real textbook, but what's the idea of mutually exclusive events? It's events that can't occur not without the other, but they can't occur at the same time, right? That was that visual diagram where the two circles on the were no overlap, right? Completely independent, like shouldn't say independent, completely no overlap, right? You couldn't be in A and also be in B, right? So another way we said that was the intersection had to be 0 because there's just no overlap. The idea of independence is a little bit different, okay? The idea of independence is, if I think about the probability of A, the unconditional probability of A, okay, that's the same as the conditional probability of A. So even if I give you this additional piece of information, which is that event B has occurred, the probability of A doesn't change at all. So how could this be the case, right? So I'll try to give you kind of another visual here as to how, get all this extra junk off the screen, how we could have two events be independent. So I'll try to kind of draw out the entire experimental outcome space first. So let's say, also make sure I'm still up there, okay. Let's say I have this huge experimental outcome space, okay? And I'm gonna try to exactly cut it in half, okay? So this rectangle over here, I'm gonna call event A, all right? So we think about what the probability of A is. Oops. All right, the probability of A is 0.5. It's half of the entire experimental outcome space. Okay. Now what happens if I also have event B, but essentially it cuts this experimental outcome space. So you can think about this entire rectangle down here is event B, and the probability of B occurring is also 0.5, right? It just cuts the experimental outcome space in a different direction. So now if I think about the conditional probability of A, so now if I want the probability of A conditioned on B, well, the equation that we had for that was this should just be the intersection of the two divided by the probability of whatever event we're conditioning on, right? Now we're conditioning on B, it's what comes after that conditional line or that given line, okay? And if we think about the visual here, well, once I condition on B, now I know that I have to be within this space. How much of that space, so the area of that space would be 0.5, that's what the probability of B is. Now what's the probability that I'm in rectangle A? Well, this is no longer a possible outcome, right? Because this area isn't in B, right? And we know, we were told that we're definitely in event B. So now the only area where we could be in A, once we've conditioned on we have to be in event B, is this kind of area here. Like I said, I try to draw this to scale, right? Well, this is now half of the experimental outcome space left. But really, if we just think about starting out, what was the probability that we had A and B overlap, or that we were in both A and B? Well, that was just kind of a fourth of this entire experimental outcome space, right? Because they cut it in half in different directions. Okay? So we can take the intersection of the two events, divide it by the probability of what we conditioned on. 0.25 divided by 0.5 is 0.5, right? And that was the unconditional probability of A as well. So this is an example of how two events could be independent, right? We can think about the idea that, you know, usually I try to give good examples of this. People could probably argue them, but my example I always give of independent events would be something like this. Let's say event A is that I have blue eyes, right? Natural blue eyes. That's event A. I don't have blue eyes, but let's just assume. So event B, let's say, is that someone is male. Right? Conditioning on the fact that they're male doesn't give me any additional information about what the probability of their eye color. Because if we look at the whole population, the probability that any one random person has blue eyes, there's no systematic differences, at least as far as I know, in terms of blue eyes among men or women, right? So it doesn't matter if I condition it on gender, because the kind of makeup of blue-eyed people in both those groups is the same, right? So that's the idea that those two things are independent. It doesn't matter if I know the one, it doesn't give me any additional information about the other thing, right? So that's kind of the general idea of independence, and then we can kind of see in an experimental outcome space what that would look like, right? So you can almost imagine those two rectangles I drew. Think about it as, you know, maybe it was something we broke down by gender and then another characteristic that is not systematically different across the two genders. So something like eye color, okay? And also if there's someone who's like a double biology major, you can check me on that. I don't know. I think that's a good example because I assume that eye color, natural eye color isn't different across the two genders, but I may biologically be incorrect in that statement. I'll concede that. So if we have this idea that these events are independent, right? So that the unconditional probability of A, right? We're not conditioning on anything here. And the conditional probability of A, right? We're still looking for the probability of A. It's just now we've conditioned on this other event B. So if those two events are independent, those two things have to be equal. So if we go back to this multiplication rule, and let's say we rearrange it a little bit. So instead of finding the conditional probability, let's say I wanted to find the intersection, right? Then I would just multiply both sides by the probability of A and kind of move this over here. Then I'd have this equation, right? So this is just that multiplication rule I showed you on the other slide, just rearranged a little bit, All right? So if that's the case, and I know they're independent events, well, what can I substitute in here? Well, the probability of B conditioned on A, this is the conditional probability of B. If A and B are independent events, I know that this is the same thing as the unconditional probability of B, right? So I could substitute this in down here, just the probability of B, and now finding the intersection kind of simplifies to all I have to do is find the probability of both events and multiply them by each other. Okay? So that's just a little bit of a substitution. Once we know the definition of independent events, we can plug it into this multiplication rule that we had, rearrange it a little bit, and finding the intersection of two events is kind of simplified. And I'll prove this to you in a second using a contingency table. Okay? But this is kind of where we're going to be starting now. So any questions at this point before we keep moving forward? Everybody hear me okay on Zoom? Need to be a little bit louder, or one person respond, hopefully? Are we all still sleeping this morning? Okay, we're good. All right. So, using this idea of independence, let's go back to a contingency table and think about, well, I can find the probability of events pretty easily from a contingency table. I can find intersections really easy. Remember, those top four left cells all represent intersections. And so I could start to find conditional probabilities from that contingency table. They're not directly given to me, but the components that I need to solve for it, right? If I don't know what the conditional probability is, I can find the probability of an intersection, and I can find the probability of the event we've conditioned on from that table, okay? So if I look at this contingency table, and I want to check, let's say for right now, I just want to check to see whether or not A and B are independent events. Well, I know if they're independent, that these two things will hold, right? I can check either one, right? It doesn't matter which one I check. If A is, it's kind of like the other rules we talked about. If A is independent from B, B has to be independent from A, right? And so I'll check this first, which is, I think this is the one I did. Yeah. Is the conditional probability of A equal to the unconditional probability of A? So what's the unconditional probability of A? If I'm just looking for that probability of A, not conditioning on anything, what should that be from this table? Well, I go down to the contingency table. Here's A. How do I find the probability of A? I don't have to so I'm not trying to find the conditional probability yet. I just want the probability of A. So remember, how do we read these contingency tables? The top four left cells are intersections. What do the totals represent? So this would just be the probability of A. Right? The probability of A is 0.6. The probability of B complement, 0.75. The probability of A complement, 0.4, right? That's what those totals gave us. So to find the probability of A, I can find this right side of this equation pretty easily. I just go to the table, probability of A is 0.6. Right? So now I know if the conditional probability of A is equal to 0.6, these are independent events. But I can't just directly grab a conditional probability from the table. We have to go back and say, if I want this conditional probability, I can solve for it by finding the intersection of the two events and then dividing by whatever I'm conditioning on. What I'm conditioning on, this was on the right-hand side of that line, right? So I go to my contingency table. I know that I can rewrite this as the intersection of these two events divided by the probability of B, right? That's what I was conditioning on. So divided by the probability of what I'm conditioning on here is the probability of B. What's the probability of B from this table? I'm going to close the door real quick. Pretty easy. Okay. So, someone in class said it right. The probability of B is simply 0.25. Right? So that's pretty easy to find. Now the other thing I need is the intersection of A and B, which would be what from this table? We said these top four left cells all represent intersections. So if I want the intersection of A and B, that would just be, yep, the intersection of A and B is in this cell right here, so the probability of the intersection of A and B is 0.15. So I plug 0.15 in here, 0.25 in here. Sure enough, if I do that math, I end up with 0.6. So this conditional probability is 0.6. And we originally said the unconditional probability is also 0.6, right? So these two events, because those two things are equal, oops, I'll show you this one in a second. Because those are the same value, that's the definition of independence. We just have now shown that the conditional probability of A is equal to the unconditional probability of A, okay? Any questions on that before I move to the next part? Okay with that? Okay. We could have also checked it the other way, right? So let's say I wanted to check it using the conditional and unconditional probability of B. Well, what's the unconditional probability of B? And when I say unconditional probability, that's really just the probability of the event, right? Because we're not conditioning anything. So what's the probability of B here? I look at B, the probability of B, we've already said earlier, was actually 0.25. So I know the probability of B is 0.25. So if this conditional probability is equal to 0.25, it would also show me these are independent events. So I think about, okay, I can find that conditional probability of B. It's the intersection of these two events, so it doesn't look any different than what it would the other way. But now I'm conditioning on A, so now I'm going to be dividing by whatever I'm conditioning on, so now I divide by the probability of A. Okay? So now I look for the probability of A, that's 0.6. The probability of the intersection, we already said before, was 0.15. I plug those in, sure enough, I get that that conditional probability of B is 0.25, which is the same as this unconditional probability of B. So it didn't matter which way I checked it. I could kind of use either way, or either event, right? I could check to see if the conditional and unconditional probability of A were equal to each other, or I could look and see is the conditional and unconditional probability of B equal to each other, right? And either way, prove to me that these two events are independent, okay? Yeah. Yep. Yeah, so right, this upside down U, right? We can think of this two different ways. We read this A intersection B, or kind of maybe a little more sloppy in the like A and B, right? So and intersection, that was kind of where I said if you look like you put a line through here, it kind of would look like an A, so that tells you it's A and B or A intersection B. Or if it's easier to think about, where do A and B overlap? Okay, oops, sorry. So we're okay with this before we kind of move to the next thing. So one nice thing about independence as well, and I think this is probably the easiest way to check for independence. This is good to understand kind of the multiplication rule aspect of it. But a nice thing that comes out of the fact that two events are independent is that when we rearrange that equation, we said we should be able to substitute in here, if they were independent, then this would just be the probability of B, the unconditional probability. So this right here has to hold if two events are independent. So if I look at the intersection of two events, if it's not simply the probability of each one of those events multiplied by each other, if these two values are not the same, then they would not be independent events. If these two values are equal, then they have to be independent. So we can actually grab these components from the table as well. So we'll go down here. There we go. What's the intersection of A and B? Well, we said this already. The intersection of A and B is 0.15. The probability of A is just 0.6. Probability of B, 0.25. Let's plug those numbers in and see if what? 0.6 times 0.25 is equal to 0.15. If you enter that into your calculator, sure enough, what you'll find is the probability of A times probability of B, 0.6 times 0.25 is 0.15, which is exactly what the intersection is, so these events have to be independent. Now, we already checked for their independence the other way, so we already knew this, but this is just like a third check you could do. And I think this is the easiest one because, instead of having to worry about dividing by, oh wait, do I divide by the probability of A or B? What am I conditioning on? Like, it's a little bit kind of harder to maybe remember that or do that. If I know that this has to hold if events are independent, it's very easy to get the probability of the events themselves. And hopefully by now, it's starting to get pretty easy to find the probability of the intersection of the events as well, right? That's information that's directly given to you in that table, okay? All right. Oh, and I'll mention this here. I won't like test you necessarily on this or kind of throw this in, but a nice kind of byproduct of events being independent are that actually their complements are independent as well. Right? So notice here, if the events are independent, this would have to hold. If the complements are independent, this would have to, right? I'm just putting the complements in here. So what's the intersection of the complements? Well, probability of A complement and B complement is 0.3. The probability of just A complement is 0.4. Probability of B complement is 0.75. 0.4 times 0.75 ends up being that intersection probability of 0.3 as well. So you can actually check to see if the complements are independent, then you know the events are independent themselves. And this is, I'll tell you the intuition behind this, right? So if I go back to my eye color example, if I think about the complements, so instead of conditioning on is someone male, if I condition on if someone's female, and then instead of looking for if they have blue eyes, I look for the probability they don't have blue eyes, right? Right? Those are independent, right? The original example where we have these things are independent. If I think about it in terms of the complements, those will be independent as well, okay? Any questions on this before we keep moving? Good with this? Okay. So let's think about how could I simply find a conditional probability using a contingency table? So if I have R1 conditioned on C2 here, what I'm really thinking about is I want a conditional probability. I can't directly grab that from that contingency table, but I know I can rewrite that using the multiplication rule, and then I can find the components on the table. So we think about, well, let me make sure because I'm probably going to get it wrong if I don't look. R1 given C2. Okay. So let's say what I want, right, is the probability of R1 given C2. Right? If I'm looking for a conditional probability, I know I can rewrite that. And if it helps, like write it vertically like I am right now, it's just the intersection of these two events. So R1 intersected or and C2. And then I'll divide by whatever the probability of the event is that I'm conditioning on. What I'm conditioning on is on that right-hand side. And so I'll divide here by the probability of C2. So write out what you're looking for, and then right next to it or right underneath it, rewrite it using that multiplication rule, right? Just the intersection of those two events divided by the probability of whatever you're conditioning on. And I'm sorry, my C's look like parentheses here, but right, let me try to, here's my parentheses, and then C2 is within that, right? Okay. So now if we go back to the table, we know what we're looking for, which is the intersection of R1 and C2 divided by that probability of C2. So what's the intersection of R1 and C2? R1, C2, that probability is 0.2. So that'll plug that into our numerator. Divided by what we're conditioning on, that was C2. So the probability of C2 is 0.5. So 0.2 divided by 0.5, right? We're just plugging those values into that equation that we had in the board, and then that should give us 0.4. Okay. Any questions on that? So I'll give you another example as well. Actually, where are we at? Let me see where we're at here. I know we're not going to make it super far into the Excel, so I want to give it, yeah, I'll go through some fun stuff. So I've kind of described events that are independent. It's sometimes easier also to think about events that are dependent, right? So sometimes the example I'll always use is, and you'll see this maybe in some practice exams and once I put those out there. But the idea is like, let's say I divided things up by political party, right? Let's say I divided things up by political party, right? And I tell you, what's the probability that in this upcoming election, like, I don't know, maybe there's a proposal on the bill that we're going to vote to whether or not we want to nationally legalize marijuana or not, right? If I told you, right, what's the probability that someone chosen at random, right, just any person wants to would vote yes to nationally legalize marijuana, I don't know what it is. I'd have to look at some of the surveys out there, but, maybe let's assume for a second it's 0.5. Let's say half of people, just for the sake of this argument. If I then said, okay, what do you think the probability if you chose someone at random that they wanted to legalize marijuana is? But here, given that, right, conditioned on that they're also a member of the Republican Party, what do you think probably happens to that probability? It's probably lower than 0.5, right? Same idea. If I said, what's the probability they want to legalize, nationally legalize marijuana, conditioned on the fact that they're a member of the Democratic Party. Well, the probability of that is probably higher than 0.5, right? So those are events that are dependent, right? Having that additional information could greatly influence the underlying probability of whatever event I'm interested in. And more often than not, we are going to have dependent events. Independent events are kind of rare, right? It has to be these things that really have there's no systematic differences across whatever we're conditioning on, right? You can think about the same thing. Instead of using political parties, you could think about using age, right? Over 65 and under 65, and then kind of voting to support the national legalization of marijuana, right? You would expect very different probabilities if I told you, conditioned on the fact that this is a 70-year-old person relative to a 25-year-old person, right? So a lot of events we're going to be looking at really are dependent. It's very unlikely we find that events are actually independent. Okay? Now, these little toy examples I'm giving you with just these really easy probabilities, yeah, we might find that things are independent because it is important that we can know how to test for it. Okay, so here's another kind of interesting thing of this idea of independence, right? So if events are independent from each other, right? In practice, we can also think about, let's say I'm flipping a coin. Each coin flip is independent from the previous, right? So I know that if I flip a coin, the probability it comes up heads is 0.5, if it's a fair coin, right? I guess maybe, right, there's like a 0.00001, it lands, in the middle, but for the sake of argument, it lands either heads or tails, okay? So we know the probability it comes up heads is 0.5, so over the long run, we know if I flip a coin a million times, about 50% of them are going to come up heads. Right? Coin flips are independent events, right? The result of the first coin flip doesn't have any impact on the second one, right? I could flip a coin and it comes up heads. What's the probability the next time I flip it that it comes up heads? Still 0.5. Right? There's no change in the underlying probability. So this idea of if I have instead of heads, let's say I flip a coin and I get like 5 tails in a row. What's the probability that sixth flip is going to be tails? Well, the probability is still 0.5 because these events are independent. Knowing what the previous coin flips were tells me nothing about the underlying probability of this current coin flip. Right? So it's no more likely or less likely that I see a tail in the future. A lot of times people kind of fall victim to this, and this is why like Kenny Rogers or like the gambler's fallacy. So the answer is no. You can simulate this in Excel if you want to. I did this at one point where you can do 10,000 different coin flips in Excel, like random number, kind of 1 or 0. Then I look at, okay, given that the previous coin flip was a tail, what's the probability that the next coin flip is a head? It's almost exactly 50%. In fact, it goes out more zeros here. I just rounded to the third. What if I get 2 tails in a row? What's the probability I see a heads? A little bit under 0.5, but really, really close. What if I get 3 tails in a row? Probably the next coin flip comes up heads, still right around 0.5. And obviously, these are going to be a little bit off from 0.5 because to truly get to 0.5, we'd have to have an infinite number of coin flips, which you can't really simulate that. And even at 4, right? 4 in a row, you're still looking at the probabilities right at 0.5. Right? And this you kind of can prove to yourself in Excel. Right? So kind of a nice little example that goes along with this. It was like, where is this, Monte Carlo? Yeah, so way back in the day, it was a roulette table. And for the sake of, if you ever looked at it, there is a green spot. but the number of black and the number of kind of red squares that are on that wheel, and I don't think not squares, they're probably more like not rectangle. I think they're actually like trapezoids. I don't know. Whatever they are, whatever their shape is, there's equal number of black and red. So we can think about this similar to a coin flip where the probability of seeing black is about 50%, probability of seeing red is about 50%. Like I said, there's that one kind of non-red or black location. We won't focus on that. So way back, August 18th, it just so happened that this one table came up black 26 times in a row, right? So the probability that occurred is very unlikely, right? We can actually think about how unlikely this is. We can almost think about these as each spin is a different event. So the probability I see black come up on the first spin would be maybe probably, event A. Event B could be the probability I see black come up on the second spin, so on and so forth, right? If every single spin is independent, what's the probability that I saw the first spin come up black and the second spin and the third? When I'm using this word and, I'm really thinking about intersections. So if I go back here we were just thinking about, where is it? There we go. No, this is what I want. Here we were just thinking about two events, but now I've got the first spin is black, and the second spin is black, and the third spin, and the fourth spin. Well, if I know that these are independent spins, right, no matter what happens in the first spin doesn't impact the probabilities of the second, I can really just take the probability of each event and multiply it by itself. Well, the probability it comes up black on any given spin is just 0.5. So I could actually figure out what that probability is by taking 0.5 and multiplying it, 26 times? Yeah, multiplying 0.5 by itself 26 times, or 0.5 to the 26th power, right? I don't know if anyone has a calculator. I can actually, all right, if we do 0.5 to the 26th, all right? So this is actually a good thing to kind of bring up in Excel because we might start dealing with this. This e to the negative means move the decimal place however many spots this number is to the left. So 8 spots. So you would take this decimal and move it over 8 spots. So this is what? 0.7 zeros and then 1. This is an extremely low probability that it came up black 26 times in a row. So what happened was, after about like 8 or 9 times, people see this come up black like 8 or 9 times in a row. You can fall victim to the gambler's fallacy, which is that in the long run, I know that the ratio of black to red roulette table spins should be 50% in the long run, right? But over any like smaller subset, I could see, different lengths of consecutive blacks and consecutive reds. So after people saw this come up 8 or 9 times, so they fell victim to this gambler's fallacy, which is the idea that, well, it's come up 8 or 9 times black, it has to come up red next time because these have to balance each other out. Well, no, each individual spin is independent from the previous, right? So just because you see it come up 8 or 9 times in a row, as long as it's a fair roulette wheel, right, the probability on that 9th spin it comes up black is still 0.5. But people fell victim and said, no, it has to be red in this next one. It said black 8 or 9 times. It can't be black 10 times in a row. So they started betting on red. Well, what happened? Well, the 10th spin came up black. Well, if the first 10 were, the 11th surely can't be. So everybody bets on red again. And this continues, right? And just, even though it was a low probability of occurring, it ended up being black 26 times in a row, right? The casino made, right, tons of money on this because everyone's betting on red and getting it wrong. And this is an idea of like, you shouldn't fall victim to this gambler's fallacy. If events are independent, right, previous outcomes shouldn't have any influence on the probability of future outcomes. Okay? This is like a big thing, kind of this gambler's fallacy. A lot of people look at this in terms of human behavior, not just like in gambling, but in a lot of different aspects as well, right? Just because I see something occur, if the underlying probability isn't changed for the next time, right, I'm going to do that thing, then I shouldn't be influencing my decision, right? So this is actually, you can almost think about it like this, right? The underlying probability that your house burns down, right, doesn't change day to day, assuming that you're not, I don't know, installing some new wiring or something. It doesn't change day to day. But as soon as someone experiences one house fire, when they buy their next house, even though the underlying probability might be the same as it was before, they're way more likely to get fire insurance, right? Well, the underlying probability didn't change, but their behavior changed, right? And that's a little bit different than the gambler's fallacy. You can think about this as kind of, there's this hot hand idea as well, where people actually take the opposite approach. So although most people fall victim to this gambler's fallacy when they're gambling, the hot hand fallacy would be the opposite idea. If I see black come up 10 times in a row, I think, well, man, has to come up black 11 times in a row. There's something about this wheel. This was a lucky wheel. Has to come up, and you can kind of fall victim the other way as well. But the other way is wrong too, because the probability isn't any more likely. It's still the same, right? If these are independent events. Where does that leave us? Okay. So we'll start a little bit of work in Excel today, and we'll kind of pick back up on it on Friday. Using this. There we go. So if you go to Canvas, Files, in-class data, I have this union data set up there now. Okay. So if we look at this union data, I've got a finalized kind of completed version. And we might use different cutoff values in class, but this kind of gives you a nice idea of what we're eventually going to do. Here's the blank one that we'll start working with, right? So you've got it zoomed in a little bit. So let's just talk a little bit. I'm going to get rid of myself here. About the data set. So it's got a bunch of different industries across from 10 years, 11 years. And in those industries in that year, it has the percent of the workers that were in the union. What's this? The percent that the union represents, union member weekly earnings, the weekly earnings of the people that the union represents, not just members, but everyone they represent, non-union weekly earnings, and then kind of the difference. I created this other variable, which was just, I took union membership earnings and subtracted non-union membership earnings to get an idea about, in these different industries, how much more, this variable essentially represents how much more money you could make in this industry in that year if you were a part of the union, right? If I was a part of the union in the combination industry in 2008, I'd make about $111 more. So I then kind of got to thinking about, well, maybe there's like something kind of interesting about if the majority of the industry is union members, right? Maybe that does something to this difference, right? Because maybe if 90% of the workers are union workers, right? It may be that, these non-union workers are paid very similar rates, potentially, even to the union workers, whereas if they're a relatively low percent, right? There's a lot more workers I can just go out and replace the union workers with, and so maybe I don't have to pay them near as much, so maybe when there's a low percentage of union workers, that gap in between union and non-union kind of wages grows, right? So I can kind of test that idea here with this data set. So the events we're going to be thinking about, if we want to break this down, instead of A and B now, I'm going to have actual events, like words to them, right? So my event A I'm thinking about is the difference in union and non-union earnings more than $100? And then is the difference between union and non-union earnings less than $100? So is this variable here? My event A would be that variable is greater than $100. My event A complement would be that difference is less than 100. I'm thinking about my event B. I'm going to define that as if I see union membership in that industry and in that year be 10% or higher, so greater or equal to 10%, that's my event A. If union membership is anything less than 10%, that's going to be B complement, right? So I've just created kind of two events I'm interested in. Their complements I've created, can get from that as well, because the complement is just anything else, right? If I define event B as having union membership be 10% or higher, B complement is everything that doesn't fit that, which is just being less than 10%. Right? So now we actually have to kind of put some values to what these events are: A complement, B complement. Right? So that's where we're going to start off, and we're essentially going to build our own contingency table. Right? These top four left cells, right? I can think about A complement, B complement. These will represent my intersections of those things. And then my totals will just represent the probability of seeing each one of these things. So, and kind of the way I did this, just to give you a little bit of insight why I chose $100 and why I chose 10%. And I can kind of put my cutoffs up here right now. So I did $100 and then, whoops, 0.1 or 10%, right? Because those percent, or actually, if I look at the data, I might be wrong about this. The data is actually written as percents, so I actually don't want to use 0.1 here. I actually do want to use 10%. So I just put my cutoffs in these cells up here just to kind of be easier. Actually, I think one of them I had way down here for some reason, so I'm just going to try to match complete file. I'll put that down here. Okay. So what I first did was, okay, well, what's the mean union membership, just to get an idea about the data. So I went over here and I found the average of union membership, right? Click on the first cell, Control Shift or Command Shift on a Mac, hit the down arrow, hit Enter. So mean union membership is about 10.7. So I didn't choose exactly the mean as my cutoff, but I chose something somewhat close to it. So we can kind of think about this as maybe above or below the mean if we really wanted to. Okay? I then kind of could look at union earnings, non-union earnings. That's just find the mean of the union earnings, which was what? Over here in column E. I then kind of found the mean for non-union earnings. Non-union weekly earnings was right here in column G. So I just selected that, found the average of that. And what's the mean difference in these earnings? That's just taking the average of this variable I created, which was the difference in union, non-union earnings, right? Just kind of looking at some averages right away. Once again, I didn't exactly choose the mean to be my cutoff. Instead of $118, I chose about 100. But by the time we get done, we'll see that I can play around with these cutoffs a lot if I want to, right? Once I get the whole thing completed, as long as I keep referencing these cells, I can change those cells to different cutoff values later on. Okay? Any questions on anything I've kind of went over so far? Okay, so 2 more minutes left. I'm going to do one more thing here with you. So the idea that what we want to do here is we want to look at every single observation where the difference in earnings is more than $100 or $100 or more, and that union membership is 10% or higher. So really what I'm going to want to do is I want to use that count ifs formula again. What's the first thing I want to check? Well, I want to see every single time that this difference earnings variable, so what variable did I look at? This difference in earnings. So I select that, send myself back up to the top. Oh. I don't want you over here. There we go. I'm then going to say, okay, what do I want to check? Well, I will only want to count the observation if that difference is $100 or more. So I want to count it if it's greater than or equal to, and then we have to put that and sign. And I said I want to use $100. Well, that value is up here. So I just selected that $100. Now, the next thing I want to check is the union membership 10% or higher? Well, where was my union membership? Go all the way over here. That was in column C. I could select it again. I'll tell you what I would do as a shortcut, since I already know the range from right here. And instead of going to the bottom and having to scroll back up on my laptop, I'm just going to type it in. I know it's in column C. And I know it goes from column C2 to C736, right? Because I can see that over here. Now I want to count it, right? The first thing I checked is it $100 or more? But now I only want to count it if it's greater than this other variable of union membership is greater than or equal to 10%. Right? So that's going to tell me every single observation that fits those 2 criteria. Right? And I'll then kind of continue this process to fill out the rest of this table. So we'll pick up on this on Friday. We'll fill out the frequencies for this table. We'll then talk about how we turn those frequencies into probabilities. And then now we've built our own contingency table, we can start to answer questions like we looked at on those basic contingency tables in the slides, okay? So we'll pick up on this on Friday. If you have any questions, feel free to email me. Otherwise, I will see some of you on Friday, and I will see some of you next Monday. Okay? All right. Have a good day.